In the morning, when I rise, in the morning, when I rise, in the morning, when I rise, give me Jesus, Jesus, give me Jesus, give me Jesus. You can have all this world. Just give me Jesus. When I am alone, when I am alone, oh, when I am alone, give me Jesus. Jesus, give me Jesus. Give me Jesus. Give me Jesus. You can have all this world. Just give me Jesus. And tonight, you've never given your heart to Jesus Christ. You came with somebody, or you heard of one of these bands, you're like, oh, I'll go check it out. And you've heard us all night talk about Jesus. You've never had a relationship with him personally. You see, we've all made mistakes. For the wages of those mistakes, it says, is death. But listen, Jesus Christ, being the King of Kings and Lord of Lords, he came down to this earth. And he went to the cross, and he bore what we deserve on the cross because of his love for us. And so now he offers it freely to each and every one of us. If you've never given your heart and made him Lord of your life and everything, make that commitment tonight. Don't walk out of here without saying, Lord Jesus, I need you. I need you. I know there's people here tonight who've never made that commitment. The hope of eternity, as I said even earlier, I've had a little glimpse of heaven in a sense. No more tears, no more sorrow, no more pain. But while I'm here, I have Christ to walk with me every single step. Thank you, Jesus. Lord God, I thank you for tonight. I just pray for our hearts. Help us to be a night of remembrance because you were here. And that's it. But all we remember is just you and the time that we spent with you. That's all it's about. Soften our hearts, change my heart, Lord God. Search my heart and try me and see if there be any wicked way in me, Lord God. I just want to be a vessel, truly purified and ready to be used by you. Thank you, Jesus. We love you. Thank you, Jesus. When I come to die.
Morning, guys. I think we'll start shortly around 8 a.m. All right. So just relax now. Do you have a chance to make a coffee? Go ahead. Please do so. So I think we'll start around 8.
Give me Jesus. Give me Jesus. When you first stand, lift your hands. Give me Jesus. You tired? This one.
All right, guys. I think let's start. So let me switch to my main screen now and um, start on this slide. So I think I would leave this slide for 1 or 2 minutes. Let me see how many of us has been signed on. Wow, I think we got at least 1/3 of the class on right now. Um, so I hope everyone is. I think everyone are doing okay. I think this is our second week already in whatever this online, and there's some quiet adjustments. So I think I'm hoping that I think you are comfortable now. For me, I think I'm start getting used to whatever this social distance, and I've been by myself almost 3 weeks without seeing anyone. In fact, I think this weekend I was asked by my daughter to go helping her out because of two grandchildren there. Unfortunately, I think Texas governor just put on the um, whatever emergency order that any driver from Louisiana must be quarantined for 14 days. So I decided not to go. But on the plus side, I think it helped me. I mean, even though this is my 20th year teaching operating system, and I've been doing operating system research and work in this area almost 30 years, quite comfortable, I mean, about the material. In fact, I can close my eye and think about, I mean, everything, I mean, especially regarding our lecture. So but then I mean, with the online teaching, I think it allowed me to learn a lot more things that I thought I knew, and especially how to deliver this content in this online manner. Also experience with a few new tools, such as I think last time when I did the quiz, I have some question already, but I have to transcribe and then put in whatever web-based type of question, which is quite cumbersome for what set of question I have. But I think right now I do some reading. There is some bulk loading. I have to put in certain format, and then I don't have to retype the whole thing. And then beside this week, we also have a faculty meeting using Zoom, whatever video conferencing. I think some of you guys probably already have some experience with other class. For me, my previous concern was I think the scalability of the Zoom system. I think since our class had 36, 37 students there, that might also a little more challenging in terms of the bandwidth. But I think yesterday we have the first faculty meeting and everyone attend. It seemed to go smoothly. So I might change or adapt something regarding for the class, but I still doing the same thing using this live broadcasting because I believe that it is probably one of the most effective way, even though the best way, I wish that we have face to face, but I think I mean, the ability to broadcast or deliver online and also do the live chat, I mean, for the feedback, I think that give us close enough, I mean, some ability for interactive. Okay, so coming back to some of the item that I hope I wish to remind you guys. I have several presentation title that's sent by you guys. Okay, I think one of the topic is virtual office, which I make some suggestion that, I mean, you can pick anything, but then the presentation should be centered around operating system, runtime, or some sort of system program that manage the hardware or doing something, with respect to the OS type of concentration. Okay, how many people can it be in one team? Um, oh, I'm sorry. this is not team presentation. This is the title for a. I think let me change this before I forgot. Okay, so allow me to do this. Your term, not team, term presentation. It's my mistake. So Carrick, I think thanks for catching this. So I owe you. I think I told you, told all my class that if you guys catch my mistake, I'm gonna pay you something. Okay, so I'll get some of the whatever, either T-shirt or some high-tech toy, and then give it to you. I mean, because you catch my mistake. It's not team presentation, is term presentation. Okay, so the title by this Friday, I already got some topics such as virtual office, which I suggest that individual to look into virtualization or virtualization tools such as virtual machine, virtual storage, virtual screen in order to put together and enable virtual office type of application. Also, one suggestion on AI for OS, which is quite broad. Okay, so I probably would allow some big topic that multiple presentation can be, uh, the same topic or similar topic. And then operating system for IoT or smart devices, VUI, which is voice control operating system. There's one person would like to do that. And then last but not least is Docker. Okay, so it's not just limited to this. I think there are some previous topic that I have given to you. So please pick it by this Friday. And if anyone don't pick any topic, okay, I will by next Tuesday I will randomly give you guys topics. Okay, I hope that you choose your own topic, because some of these topic, it could be your career, it could be your future business. Maybe you can venture out and start create some sort of product or a system on that area that you can deep dive into. So I think it gives your resume stronger, instead of you have a common whatever background just like everyone else. So if you start doing something, I mean, deep dive into certain technology, and then maybe perhaps extend that into whatever spatial study or something. I mean, it could be your own career. Also, the presentation that previously I asked you to just video yourself and put on YouTube, I changed my mind. Okay, Ronco asks, uh, do we message? Yes, please. For anyone who picked your own topic, who already picked the topic, please send send the topic to me via email. Please send to naibox@gmail.com. Okay, the email that I always recommend you to send to me. Don't send to tech email, because I got the whole bunch of junk mail, other work mail, and everything else. Okay, so sometimes it may just slip through the crack, and I might not be able to see those. But if you send me to Gmail and then put the title as term paper or term presentation, something like that, I can easily do the search. Okay, so thanks, Ronco. I think another question is this topic from Christian, something that we have some interest in, that would have something to do with our direction for our major. Yes, but Christian, but you also have to, I mean, the topic should touch upon aspect of operating system runtime, such as not just OS, virtualization, cloud computing, those sort of things. Okay, because otherwise it's not justifiable. If, I mean, if you do something totally, for example, if you want to look into the hardware aspect of, for example, the self-driving car that has nothing to do with operating system or the system to manage. Okay, it may not be justifiable. But then if you do, let's say, self-driving car and talk about the runtime system that glue together all these sensor, okay, or manage the sensor, optimize the way you do analytics, all those sort of things based upon runtime operating system. I think that is totally justifiable. Okay, so thanks for the question, Christian. So I mean, coming back to the presentation, I changed my mind that since yesterday I have good experience with the Zoom video, and with the Zoom video you can share your screen, you can have participation, and yesterday we have close to 20 participants, and I think it still work well. So I'm hoping that we're gonna instead of I mean ask you to upload to YouTube or do yourself video. I like to schedule you to present during this class or online presentation. So instead of you we do YouTube live on that date. Okay, I'm gonna schedule you Zoom video conferencing, and then in that case we can have some interaction, because I believe that when you guys present something, when I ask you some question, I think it helps stimulate more thoughts, some more idea, and in fact, I could point some of your presentation or aspect of your presentation to the topic of our class. So I see that it's a lively kind of discussion. In fact, personally, if you ask me, I enjoy most during your guide presentation, because that allow me to start seeing the way you grow. You know, I mean, doing your own research, and also start thinking or put your thought to connect, you know, the idea of some certain application to what you learn from the class. Okay, so I think in that the due date of the presentation gonna be on April 28th. I saw, I think another question Christian has asked, for example, I would like to work on virtual reality. I need to talk about the topic as well as the component software, hardware, and make up the OS. Yes, Christian, let's do this. I think anything that when you discuss about specific thing, I mean, we can spin on the OS aspect, you know. I mean, for example, right now nowadays most game system that when you guys play against other people, the scalability aspect of how to scale whatever those game system up. Okay, I think it need or require certain techniques, you know, with respect to distributed computing, cloud computing, and operating system all working together. So if you spend on the aspect how, you know, those virtual reality, you know, like the server side or the client side, and how this operating system communicate and manage, I mean, various resources. I think that that might be some good idea that you should explore. So why don't you do this? Let's schedule maybe perhaps either Zoom or Skype discussion. I mean, more detail. I think that that could be potential topics. Okay, so I think coming back to the term paper presentation, um, I lean more toward Zoom video, because also Zoom video you can share your screen presentation as well. So I think using these video conferencing tools, I think that would also help your career. In fact, when I was the software engineer and the developer as well as technical lead in industry. We work with a multiple site or campus, okay, working all together. So I think using have ability to master video conferencing is quite useful. So I think another benefit that when you use video conferencing whatever tools, I think it would help your future. And also Zoom can record our video so that I can later on upload our class presentation to YouTube and Moodle. Now let's see, there's another question from I don't know who this is, MJA M M Valdez or something. Is there a certain time that you want us to make with respect to what? Can you reveal your real identity, M Valdez? I think so. I think if you type some more specific thing, I'll answer you. But let me move on. Regarding to the quiz, okay, the quiz will be posted on tomorrow or by Friday, and you should conduct the quiz by midnight. Yes, there will be limit time. Again, I think it's around. I have not made decision yet, so I'm put together the question. So I want to give you enough time, but not open ended, because the quiz also um, help validate your learning and also your attention to the detail. Okay, so ballpark, I would say that I would give 20-minute limit time, but then if I have more question, then I might giving you more. Okay, so Christian asked about presentation. What is our time frame? The due date is gonna be April 28th. Okay, it's gonna be the first day that I will schedule you to do presentation, and each person I would allocate around 10 minutes plus minus. Okay, presentation. Just do the good work, because I think once you start doing research, I mean, try to gather the crux or the main idea of the presentation. So I think I would write some guideline about your presentation and post on Moodle. All right. Okay. So I want to know, I think there's another question. I wanted to know if there's a certain time limit you want. Well, in terms of presentation, it's around 10 minutes. Okay. But in terms of the quiz, it's probably 20 minutes. 10 minutes, I mean, plus or minus. I think it's based on the content and how whatever interesting stuff that you do presentation, but then try to make sure that don't go over, I mean, don't take too much time. 10-15 minutes I would not blink, but then if you want half an hour, I think it's that way too much. Okay, it's gonna start bore people, boring people. Okay, so I think that's what that probably the estimate time that I would request you guys to stay with. All right. Any other question? I think please feel free to type any question. I have another screen that I can take a look, because for my main presentation right now I'm using my display capture, so it covers the entire screen. So I think I have to have another screen on my left hand side that I would use to read your feedback. So again, I think this is example of the Zoom. Some of you guys probably have used the Zoom, and this is what we used, I mean, yesterday among all faculty member, and it's our first time that we have everyone attending this. So we kind of kidding to ourselves that maybe perhaps in the future we all should do the online or Zoom conference call. Okay, so that we would have a perfect attendance. Okay. All right, okay. Now let me capture what we have covered so far before we continue on our CPU scheduling. Um, I think we start off, we switch over from middle of chapter 3, okay, coming to CPU scheduling, which in fact is process scheduling. As I mentioned to you before, the mechanism in operating system with respect to scheduling or scheduler, there are long-term scheduler and a short-term scheduler. The long-term scheduler or job scheduler that would admit job into job pools, okay, and then some of the job are immediate job, so those will be forward immediately to ready queue. Some of them are scheduled job that run at certain time. It's gonna be store or cache in the job pool until the time reach, or the time reach to whatever that scheduled time. So I think in terms of long-term scheduler, the scheduler will run every now and then, maybe every few minutes or minutes. Okay. However, the short-term scheduler run in millisecond or microsecond. Okay, because it need to make decision to swap in, swap out. Which job that ready or reach to the time limit, and then we'll take it. We'll take the CPU back and then put in ready queue and wait for the next turn. Or some job that call system call or make IO operation, then it's gonna go to the wait queue until the IO operation complete or you have an event that those event is ended, okay, then that process will be wake up and then put back in ready queue. So the in fact, let me just get my pen, the pointer option to be pen. So in fact, this area is a uh, related to short-term scheduler, okay, that basically it manage various states of various process, and each process has its own state, whether it's ready to running and running to waiting again. So I think the life cycle of each process gonna go through various state and various queue, okay, so that all the way until it got terminated. Okay, so then we continue on and discuss specifically on a short-term scheduler or CPU scheduler or process scheduler. Before we start deep dive into, the scheduling algorithm, then we have to know our objective. Okay, what would we like to achieve in order to do this scheduling? Okay, whether we want to maximize the CPU utilization or maximize throughput, okay, or maybe perhaps minimize turnaround time or minimize waiting time or average wait time, or last but not least, in terms of interactive system or personal computing, you may also want to minimize response time. Okay, a lot of these scheduling criteria, some of them may be conflict. I think against each other. If we want to, for example, maximize CPU utilization, in that case, that may not be able, we may not be able to achieve minimum turnaround time or wait time, because CPU will be shared among more processes or application. So therefore, each of the process may not have large enough resource to work on. So therefore, it may complete the task, slower than. So it's all depend on the requirement. It's all depend on the objective in which you want to achieve. Okay, but in order to evaluate each of the algorithm, then you have to know the criteria specifically. What does it mean by wait time? Okay, so I think the definition of wait time is amount of the total time of the process that being waiting in ready queue. So it summation of all the wait time, because given process, okay, that process may be in and out CPU many times and then go back to ready queue and wait again, or go back to waiting queue. So in that case, the summation of all wait time will calculate or count toward a given wait time for certain process. Okay, and I think as I told you, I think this we still review what we covered last time. Certain criteria we want to maximize, certain criteria we may wish to minimize some of those criteria. Okay, then we start discuss three simple algorithm. Okay, the first one that commonly we have seen um, so many, I think in fact when you go to McDonald's or many places, normal practice, for human or scheduled thing to do is first come first serve, because it seems to be the most fair or the fairest. Okay, because whoever arrive first, then that person should be serviced first. But in terms of computing, it may not necessary, because sometimes, if you schedule the first job coming first and then let them being served first, okay, we may not get the best result. Okay, um, and also I think therefore, we discuss the alternative solution, uh, for example, SJF or the shortest job first. Okay, in terms of this CPU scheduling, either it may be non-preemptive or preemptive version, where the non-preemptive version is that we let the job to execute until it complete or relinquish the resource by itself. Okay, for the preemptive one, operating system will monitor that task or the job, and then at certain event, for example, when the CPU time expire for that given process, and that process may not complete the job, In that case, we may take away the CPU. So that we call preemptive. Okay. So I think the slightly different between SJF and SRJF is that the shortest job first, okay, is an alternative CPU scheduling algorithm that address the issue of the first come first serve, because the first come first serve, when you have the long, very long job that come first, okay, it may create a convoy effect. I mean, for example, in this diagram you see that we have P1 coming, I mean, first, and it take long time, like 24 units time, okay, and versus P2 and P3 take only 3 unit time. In this case, even though, I mean, it complete all job complete at time 30th, but then job number 2, P2 and P3, it may experience long wait time, okay, because it has to wait for P1 to complete. Versus, I mean, if we slightly adjust first come first serve and apply the shortest job first, okay, let's assuming that they all arrive at the same time, then we schedule P2 and P3 first, and then P1 later on. Since P1 already take a long time, if it wait a short period of time, uh, the the time that waiting, okay, it may be insignificant, okay. So therefore, for human experience, people may not feel annoyed, okay, because of the wait time. Versus P2, instead of it has to wait for 24 unit time, okay, it can start right away, only 3 unit, and then P followed by P3. So therefore, in the first case, first come first serve, even though exactly the same job, the average wait time of first come first serve is 17 units. Okay, I think we already worked on this, and you can go back and review. Versus, I mean, slightly different adjustment by apply we call priority scheduling. Okay, this priority scheduling, we use certain factor as decision making factor. In this case, we use a CPU burst or the shortness of that job, okay, in order to select which one go first. So in this case, we reduce average wait time down to 3, okay. So it's significantly different. Therefore, I think we could get some or obtain performance improvement, okay, or whatever the main objective improvement significantly. I mean, with the slight difference. Now, the alternative version of the shortest job first by apply the preemptive kind of mechanism we call the shortest remaining job first. Okay, that means when we schedule the job to run on CPU, not only we choose the shortest job, okay, but also we look into if we have a new arrival job coming in, and then the CPU burst of the new arrival jobs, okay, is shorter than the remaining tasks of that given the current process that running on CPU. Then we wish to preempt that current process out, and then let the new job that's shorter than the current job, okay, to run on it, okay. So I think last time we show you, we also have significant, I think we have slight improvement. I think, I'm not sure, I think it was 3 or 4, right? Maybe 4 uh, when we do the shortest job first, and then when we apply the same thing for the shortest remaining job, then we get 4, we get 3 instead of 4, okay. So I think this is what we discussed last time. I want to warm you up before we continue on. And then last but not least, before we end previous class, we talk about how to predict the CPU burst, so that we can use them as a factor in order to make decision which job we want to schedule, specifically for the priority type of scheduling, like the shortest job first, or the shortest remaining job first, okay. And quickly review on this, okay. Tau n plus 1, okay, is defined as the next predicted CPU burst, okay, which is at n plus 1, okay, is equal to alpha multiplied by Tn, where the Tn defined as the actual CPU burst, the CPU burst that you test and measure, okay, plus 1 minus alpha multiplied by tau n, which is the previous predicted value, okay. So in this case, this formula, it based on the accuracy of this alpha, okay, and it somewhat compensate to the predicted value, which is 1 minus alpha, where alpha it could be from 0 to 1, okay. So in that case, we can start off, if we start do this prediction and measurement, we can start off alpha equal to 50% of 0.5, okay. So in that case, the weight of the actual uh, CPU burst versus the predicted one, it equal, okay. But then when the times go by, then we can start monitor the differences between the predicted and the actual value, and then start adaptively adjust the alpha, okay. So in that case, once you start expand or you run this prediction, okay, process for quite a while, then you can start converge between predicted and the actual one, nicely, as shown in this graph, okay. So I think this is one of the techniques that one can apply and then estimate or predict the next CPU burst, so that you can use all these prediction in the CPU scheduling, okay. Does it make sense, guys? Okay. um, so I think that is end of last lecture, that before we continue on. Today we're gonna make discussion on another common CPU scheduling called round robin. Okay, but before we get into those, let's start discuss the issue in priority scheduling. As you've seen that the priority scheduling, such as shorted job first or the shorted remaining job first, both are priority scheduling. And what is the priority scheduling? Priority scheduling is a scheduling that based on a driving or decision making factor, okay, such as the length of the CPU burst, in which in the case of the shortest job first, which one is the shortest, okay. But what are potential issues that we may face, okay. One of which, let's imagine that if your job queue is just so busy, you have job coming all the time, okay, so that your queue always full. Now let's say that you may have a longer job in the queue, and then you have a lot middle job and a lot of smaller job keep coming. So in that case, the longer job may be, let me just shut off this thing. I'm sorry, guys. The longest job maybe just wait forever. That means it lead to starvation, meaning that maybe some process, longer process, we may not get services at all. Okay, so with that, let's define a priority scheduling formally. Is a scheduling in which it uses some decision making factor, such as a priority number, perhaps associated with each process, maybe perhaps specifically for the shortest job first based on CPU burst, so that the CPU will be allocated to the process in the highest priority. Okay, the small, may lot of time the priority scheduling use the smallest integer as the highest priority. Okay, in terms of priority scheduling, it could be either preemptive or non-preemptive. Okay, so it's up to whatever that the algorithm developer who you want to choose, or maybe based on situation. Because let's say that if you compare between the shortest job first versus the shortest remaining job first, the only difference, the similarity is both look at the CPU burst and then compare which one is the shortest, okay? But then the shortest remaining job first is the preemptive one. Now, if you think about if the preemptive kind of mechanism, what is preemptive? The preemptive is you want to take away that job CPU from that job. What does it mean? Then you have to perform context switching. What context switching mean? Meaning that you have to stop the process. Then look up process information such as process ID, process status, PC program counter. You guys still remember program counter is the current address to the current location of the location of your current instruction that your process executing. Okay, so that when we suspend this process, we have to remember this PC, so that once we resume its execution, then we'll use the next instruction, okay, that point by this PC. Okay, so in that case, the context switching, you would have this patch latency that we discussed last time, which means the overhead in which you have to save and restore the process. The overhead that you have to flip from the mode bit from user mode to kernel mode or kernel mode uh, back to user mode. And also the overhead to jump to the instruction that you want to resume execution. So therefore, some preemptive scheduling algorithm, if you look precisely, the preemptive mechanism may outweigh or kill the performance that you gain. However, if the preemptive mechanism is insignificant with respect to CPU burst, okay, then in that case, you may just choose the preemptive version. So I think to choose whether which one you should apply preemptive or non-preemptive, I think everything can be calculated, analyzed, and engineered. Okay, does it make sense to you guys? So the only thing that when I do, by the way, guys, when I do online, the only thing that I can tell is that all the thing that I like in class teaching, because a lot of time I do body language. I read you, I look at you, and then I'll see, you know, your response, your body language. Sometimes I can tell whether you totally lost or you pay attention or not paying attention. So I think in this case, I'm hoping or I'm praying, I'm begging you guys to pay a little attention to, you know, this online class, okay? Because I think it's a challenge, but also let's take this crisis to be opportunities and work together, fight through this, you know, challenge, and then we'll win together. All right, guys. Now, continue on the priority scheduling that we discussed. As I mentioned, the shortest job first is a priority scheduling, where the priority is the predicted next CPU burst time. Okay, that's why I think we talk about how to estimate the next CPU burst time. The main issue of the problem is starvation. Okay, which means if you are in the situation that you have a lot of job, coming to your system in ready queue, the longer job, okay, if your CPU always busy, the longer job, if you don't do anything, it could wait forever, okay, that lead to starvation, okay, which means the low priority processing may never get executed at all. How do we solve this problem? Okay, one simple technique we call aging. So the solution is aging, which means as the time progress or the times go by, then we will increase the priority to that unfortunate process. Okay, for example, if we have longer process and then we use a priority or integer indicate as a priority of that given process. Let's say that the longer process may start off as number 10, okay, versus, you know, you have shorter processes, okay, that may be their priority is number 0, 1, or 2 based on the length of each job, okay. I think at one turn, if one process get kind of chance to execute, okay, then the longer process, maybe perhaps if you have whatever the number greater than 5, then you would deduct by 1 each time, okay, so that you can apply the aging solution in a way that at some point the priority number of the longer process will go, you know, as low and then have higher priority as, you know, the shorter job. So at some point it would have chance to execute. Um, so typically, you know, in midterm exam, I would ask you guys, you know, what is the priority scheduling, okay, and then what are potential problems that one may face, and then last but not least, what are possible solutions, okay. So since we don't have, I think I scrape off the exam, okay, and then having only the quiz. So please be honest to yourself. because the quiz will tell me whether you learn something from the class or not. Grade is not the most important things, guy. The most important thing is, your experience, your learning, your knowledge, because your knowledge will go with you forever. The grade after you graduate, you get the job, would your grade be important? Probably not that much. It may be a ticket, for you to enter or allow you to have some interview. But if you have no knowledge, okay, then the interview you may get killed. Some question you may not be, if you don't pay attention, you don't learn something. You may not be able to answer those questions. So so you get only one leg into the door, but then you will not enter the door. But then if you learn something, I think it's all gonna be win-win. That means you get good grade and also you have knowledge there. Okay, so guys, let's work together. All right. Now, so I think the next scheduling algorithm that I want to discuss, which is probably one of the most common also, and some of operating system use or apply this round robin. Okay, I believe that Linux has some sort of a flavor of round robin with combination of solved real-time system. Round robin is similar to first come first serve, but then first come first serve is non-preemptive. The difference or the major difference between round robin and first come first serve is that each process will give a limit time slice we call time quantum that it will execute on CPU. If it can complete because the CPU burst is longer, then it's gonna preempt out and then it's gonna go back to the ready queue again. So let's take a look more detail on how round robin is defined. Okay, so the definition of this round robin algorithm is that each process gets a small amount of CPU time. We call time quantum. Usually maybe 10 to 100 milliseconds. But I think this is just like 5 to 10 years ago. Nowadays, if you have faster processors, okay, super fast, then maybe some of these number may be reduced into microsecond. It's all depend on how do you engineer and see um, the the overhead that may impact your total performance. Okay, that's why I think I emphasize to you that the concept is the most important thing. Don't try to memorize this number, okay? Because number will change. In near future, technology will grow, advance, tremendously, increasingly every year. So I think all the number will change. I think this year versus next 10 year, from millisecond maybe to micro to nano to picosecond. Okay, but the round robin, as I mentioned, each process will get a small unit time or CPU time to execute, and then after this time is expired or elapsed, the process is preempt and then take that process back to wait in the ready queue again. Okay, so therefore we can calculate or estimate if there are n processes in the ready queue. Okay, then we can calculate that if, let's say, given time quantum is equal to q, then each process will get 1/nth of the CPU time chunk at most q time unit at once. Okay, so therefore no process will wait more than 1 minus q time units. Okay, so in fact, the round robin, the performance is heavily depending on the queue, okay, which time quantum, because not only the process has to wait for the wait time or in the ready queue, okay. Every time when you preempt the process, you have to factor in the dispatch latency or context switching overhead, okay. So I think you need to be mindful and think about those situations. All right. um, so in terms of the performance, let's say that if the queue is super large, okay, it's large enough that larger than any processing um, time burst time, CPU burst time. So therefore it's gonna look similar to first come first serve or first in and first out. Okay, the same thing. Okay, But then if the Q is very very small, okay, then then it may impose a lot of context switching overhead, okay, which may lead to too high, and therefore your system will suffer from performance. Okay, does it make sense? All right, so I think this is round robin, which is not very difficult at all, the concept. So let's take a look at some example. Okay, for example, let's say that if we have a given load pattern, okay, P1, P2, P3, and P4. Okay, it's coming to our system, okay, where let's say that assuming that they all come at maybe time zero or next to each other, but it's queued up like this, okay, then the burst time, CPU burst time of P1 is 53, P2 is 17, P3 is 68, and then P4 is 24. All right, so let's say that if the time quantum is equal to 20, therefore if we draw Gantt chart, okay, by the way, Gantt chart is one ways one tool that would help us to manually evaluate, okay, how the our algorithm will perform. Okay, so in this case, let's say that we have the Q equal to 20, so therefore P1 will start execute, but it requires 53 units, or it only given 20 units, so therefore P1 will execute for 20 units and then go back, okay, to ready queue again. So now P1 will have 33 left here, okay, because it already scheduled and then run for 20 unit time. And then next is P2. P2, even though we allocate 20, but then it requires only 17. So therefore P2 will complete at time 37, okay. So right now, I mean, P2 is no longer need any more CPU. Next is P3, 68, then it execute 20 units. So now from 37 to 57, okay. Then we go back here. So here we have 48 left, okay. And then the next one, then we have P4, which is 24 units, but it execute only 20 units, so it's 57 is go to 77, and then P1 will schedule again, okay, and then P1 will execute another 20 unit, P3 execute another 20 unit, and then P4 execute only 4 units, okay, because it got only 4 left here. So therefore, it's from 117 to 120, 121, okay, 117 to 121. And then after that is P1, P2, P2, okay. So in this case, we maybe perhaps in this case, to simplify the problem, we may make assumption that context switch time for, I mean, between these two processes, okay, is negligible or zero, okay. So therefore we can calculate wait time, okay, total wait time. So in this case, what P1 wait time? Let's say that it's all coming at zero. It's gonna be this, right? Plus this, okay. So this one is gonna be 77 minus 20. The wait time of P1 is 57 plus, okay, not yet, guys, okay, plus what? Then then it go back to waiting queue or ready queue again, and then we'll wait until 121 and execute again. So it's 121 minus 97, so you're gonna get this one is 4, okay, 11, 11 minus 7 is 44, okay. So the total wait time of P1 is 47 plus 44 equal to this is 11, and then this is 9, 10, okay, so 101 units, okay. Then P2 wait time is 20, right? P2 wait time is 20. Why? Because let's make assumption that they all arrive at time 0, okay. But if the arrival time is different, okay, then you can have to factor those things in. let's say that if arrival time of P2 is 5, then the wait time of P2 is 20 minus 5, which is 15. Okay, what about P3 wait time? P3 wait time is equal, let's see, here it start here, which is 37, and then this one, and then plus this, and then plus this. Okay, so I think you can sum up. Okay, and then P4, the wait time is 57. Okay, then you can sum up the average wait time. Okay, so in this case, let's say that the same similar exercise to previous techniques. Okay, I mean we all can calculate any scheduling criteria. Okay, make sense, guys? Okay. Now let's take a look at the effect of if the Q or time quantum different values. Okay, let's say that if context switching time CS is context switching time is negligible. Okay, then the round robin is fine. But then if context switching time is significant, let's say that if it's 4 units, okay, then it's gonna eat up, I mean, some amount of time, okay, add on to the wait time or whatnot, okay. So if the time quantum is equal to 12, given process, if the process has required 10 units of burst time, then you have zero context switching. What if the time quantum is 6, then it will execute at 6 units, and then it's gonna be the CPU gonna be taken away, okay, and then it will schedule again. So context switching time is 1 time. If the time quantum is 1, then you can just slide, each of the execution unit is 1, then you're gonna have total 9. So therefore, if the context switching time has some overhead, okay, then you have to calculate. I think this is the formula in which that when the context switching time is significant, the total time it will be equal to Q multiplied by number of whatever time slice, okay, that you're gonna execute, okay, plus context switching time multiplied by the total context switching time, okay. And normally the T quantum time, I think if you have based on how many processes you have, okay. So I think in this case, if you have one process, easy to calculate. But then when you have more than one, then you can have more. Make sense, guys? Why don't we do this? I think now let me quickly review. I think all this, I mean, even though you work on round robin, I mean, you can perform, evaluate which CPU scheduling criteria, which one will perform better. So I think the key thing is using if we, so for example, use this criteria, turnaround time. So in that case, I mean, what does it mean by turnaround time? If we're gonna evaluate the round robin versus first come first serve versus maybe the shortest job first, okay, and maybe based on turnaround time or average turnaround time. So in that case, the definition of the turnaround time equal to the amount of time, okay, to execute the particular process entirely. That include the wait time. So the calculation will be the completion time or finish time of that given process minus the arrival time. Okay. So now I think normally I have team working on this. I think now is maybe perhaps good time to take a break. Okay, some of you guys may go ahead and take a break. So let today take a little long break. Okay, maybe 7 minutes. Right now my time is 8:53. Okay, maybe let's take 10-minute break. We'll come back around 9:03. But then don't just take the whole break. My point is that, okay, let's say that you guys pick your favorite number between 1 to 7, okay, and then work on the round robin algorithm, okay, by drawing this Gantt chart, okay, and then calculate the average turnaround time. So in that case, you have to calculate each of the process turnaround time, okay, and then sum up and then divide it by 4, okay. So what I'm trying to do is that just work on something like this, okay, by applying or using that question, okay, and then calculate each of the process turnaround time, okay, and then eventually calculate the average turnaround time by sum up of all the turnaround time for each process divided by 4, okay. So I'll give you let's say 10 minutes from now including the break, okay. And when we come back, I like to, if you guys, any one of you guys finish, please type whatever the average turnaround time that you be able to calculate. Just pick your favorite number, okay, which is 1 to 7, and then and that number would be Q or time quantum, okay. And then use this time quantum to draw the Gantt chart, work on round robin, draw the Gantt chart for like how P1, P2, P3 kind of execute, make assumption that there is no let's say that, I mean, by this point, I mean, first let's ignore the context switching, but we're gonna calculate how many context switching, okay, and what is the total turnaround time. I mean, for example, let's say if you pick number 1 here. So in that case, when you draw the Gantt chart, okay, then you're gonna have P1 execute, and then next is P2, and then next is P3, right? Next is P4, and then you have again 1, and then P2, and then you don't have P3 anymore because you already finished 1 unit here, right? Then you have P3, etc. Okay, and then keep doing this, okay. Then you can calculate, you know, I mean, the turnaround time. So pick your favorite number, okay, from 1 to 7, okay, and then work on this problem, okay. And then once you're done, so please type or chat what is your result, okay, based on the problem that you pick. The Q is I mean, from 1 to 7, pick one number. Make sense? Okay, so right now is 8:56. We'll come back at 9:05, okay, and then I'm gonna review the result, okay. The reason why I'm showing you this, okay, or I want you guys to do this because I also want to compare. Let's say that if Q different, would the same problem, that the result of the same problem would be the same or not? I would say no, okay. So I'll show you next, okay. So let's take a quick break, okay, and then when we come back, then we'll continue on. So I think I would leave this screen as if, instead of I'm switch to be right back, okay. So we'll come back at 9:05 roughly, or 9:07, okay. Right now it's 8:57. Okay, so take a break. P4 is 7, right? I just I didn't know that it's auto switch when I go to check how many you guys attending. I think I'm so proud of you guys. We still remain the same number, very strong. Even though I wish we have more, but 8 o'clock and online. Obviously, we can't force everyone to attend, but hopefully, someone will attend or watch the video. So today we have 22 out of 36, 37, which I'm quite happy. So I'm so proud of you guys. Word of God speak, would you pour down like rain, washing my eyes to see your majesty. Be still and know your endless grace. Please let me stay you guys have any question, you can type on this chat room, okay? The live chat. But if you already have some result, again, guys, don't peek to the next slide. The next slide is answers, okay? But then, I just want you guys to go through exercise. Each of you guys may have some different numbers, okay, based on different Q. So I think my point is that uh, given one algorithm, okay, even though the same workload, the result may not be exactly the same, okay? So based on certain parameters, okay, it may result differently. So let's work on. I think we still have roughly like 5 minutes. Okay, so I'll wait. Okay, before I show the result. But if any of you guys finish, go ahead and type on this chat. Okay, and then tell me which queue you pick, and then what is the total average turnaround. This is turnaround time, guys. not the not not the wait time. Okay, it's just something different that I like you to kind of practice. Good job, Bryce. You're quick. Hey, Carrie, don't forget to remind me, okay? I owe you something. I think you caught me on one of my PowerPoint that is supposed to be term presentation, but I mistake type as a team presentation. Okay, so um, make sure just remind me. In case we see each others, yeah, I got a few more topics. Okay, let me just quickly read through. I think one has picked term paper presentation. Let me check a look. Another Docker is okay. I mean, if you guys do Docker, make sure that touch upon the concept because Docker is a tools or implementation of the concept called container, okay, or containerization. Uh, Google and then do some reading. In fact, Docker is quite popular, very popular nowadays. I think if you know how to use Docker, NoSQL, MongoDB, PHP. Oh boy, I think the sky is unlimited. You're gonna get easy job. Okay. In fact, right now I think I have more time to think, prevent me to travel. So I think it's allowed me to start learning more and more. So let's see. Okay, I think maybe 2 more minutes. Okay. Then I gonna review the result. Anyone, beside Bryce, don't be shy. You can type what is your average turnaround time. Let's see what is the average turnaround time for Bryce is um, 70. I suspect it's 9. Okay, so I think we'll see. All right, guys. So I think let's resume the discussion. Okay, I think you guys should have enough break and exercise. Don't give up. You can continue work on whatever the class exercise that I asked you. I think it would help you to some sort of think about what you learn and put together the solution. Okay, I think this is the mental practice. This is good because when you do multiple times, then it's natural you can start getting this idea within yourself. Okay, in fact, I mean, you can apply to different other techniques. I mean, as I mentioned to you, I used to work for industry for AT&T as a solution architect or the team leader or technical team leader. Some of these background, like how to calculate, how to um, do some analysis, map the physical thing into logical thing, and then come up with formula or way in which that I could estimate, something, some quality of service before actually build the system. You can save a lot of cost, you can reduce a lot of potential problem, and then minimize the churn. Okay, so trust me. Um, in fact, I mean, once a while I get invited as an advisor to or consultant, okay, to some company of my colleagues, okay. Some of them, I do it for free. Some of them, there's some small fee that I sometimes occasionally provide some consulting service. So I mean, now let's just summarize what we have here. So I think if you have a different queue, the same, exactly the same round robin algorithm, and then making assumption that if context switching time or this patch latency is insignificant. In fact, the result is different. You can see that if the time quantum q is equal to 1, you got 11, okay? And time quantum is equal to 2. Now the average turnaround time, it go up to 11.5, okay? Um, Good job, Bryce. I think you got 7. All right, and then now, I mean, if quantum time is 3, it go down, go up, okay? So I think as the result here, as the exercise that I asked you to do, I mean, so different person may have different numbers there. So therefore, I mean, here we have to pay attention to the right cue. Um, I think there's another. This is Garrett. Okay, average is 6.5. Slightly different. It's okay, Garrett. Okay, I think the point is go through this exercise. Maybe we'll miss some information here and there, but I think basically I like to make sure that you guys grab some idea working on, I mean, on the spreadsheet or worksheet, like drawing some Gantt chart, and then come up with something, you know. So um, I think practice multiple times. I think it would help to lead to mastering. I mean, these techniques. Okay, and in fact, not particularly to this round robin. You can apply to any techniques once you start understand the nature of that mechanism. Okay, then you can apply and then start do calculation. So I think my point to you all is that in the future, you don't have to wait until you build the system and then test the system out. What if it does not work? Then do you have to go back 2 or 3 months and start working on it again? Your real world problem, it doesn't mean that one day you complete. It may take you a week or a few days or multiple months. Okay, and then if what if you could figure it out? You can do analysis and then predict the result, future result. In that case, instead of you going to the wrong direction, I mean, you can turn around and tweak the solution so that you can come up with better solution. So I think the takeaway that I'd like you to grab uh, from my lecture is not just like particular to round robin or to shorted job first, but the concept in which you can evaluate the performance. Okay, that would lead or help you leading to performance optimization or addressing the performance issue or quality service issue of the, the, the product or the system that you work on. Okay, trust me, I think it helped tremendously. It helped me to move up, to the leader quickly. I mean, that I'm just uh, the guy, immigrant from Thailand 30 plus years ago, and then went to work for international company, prestigious as AT&T, okay, and climb up the rank, compete against, my peer that either local or and also internationally. Some of them, I have a colleague graduate from Carnegie Mellon. We don't have anyone from MIT, but the guy that share office with me, I think he's from um, University of Washington at St. Louis. I think he's, in fact, his buddies is I don't know, Sergio Brin or one of the Google founder, because 20 plus something years ago when we were together in the office, I think he kind of the traditional kind of hacker look with the ponytail, and he point me to Google website that Google weren't as Google today. He said that, hey Box, take a look at this Google, the search engine. It's pretty cool. I don't know, I mean, what else? I mean, I mean, you can do, but I think they have a a whatever it is trial website that you can search things on the web and it crawl the web. Okay, previously, before Google, being Google today, before that, I'm not sure you're old enough. There is a Yahoo, Lyco, and a few other search engines. But anyhow, let's move on. I think the exercise that I'm asking you to do is, I think it would helpful for the future. In fact, it's just something that I've seen or done in the past, mostly from my professional experience. Okay, when I was student, I never do this because most of my teacher or professor they never have industry experience. Okay, fortunately, I have even not very long, close to 10 years, but I play some significant role in industry as the technical lead or the solution architect for international corporation. That's why some stuff that work well, I would like to share with you here. Um, Besides, I mean, we talk about so far. We talk about simple first come first serve, shorted job first, shorted remaining job first, round robin. But there are some sophisticated type of scaling policy, such as nowadays when you have this mobile phone, okay, or smartphone, or any device that you don't have power plug in. Job scheduling also play a significant role in terms of energy saving. Imagine that if you schedule the job in a way that the job will complete and then use smallest resource. Even though maybe let's say it use the same resource, but then it take less time to complete. So therefore, you have more time to do something else. Okay. So in that case, I mean, some other policy not only not only for task completion or shorter turnaround time or whatnot. Energy aware scheduling, I think it quite plays significant role. And some of these scheduling techniques could be your term paper term presentation topic. The last another bullet list is called reliability aware scheduling. I'm not sure you know my research. In fact, 20 years ago when I came here, and I decided to pick on the research, which is my background is high performance computing. Okay, but then when I was in industry, the issue of reliability, stability, and robustness of the system play an important role in my career. So therefore, when I came back to academic, I'm got inspired by my previous work or responsibility, mixing reliability aspect to scheduling, because in the past all scheduling, especially in high performance computing, is based on the shortest execution time, is based on the performance. But then in high performance or supercomputing, the way they try to speed up by increasing number of CPU or cores. But then at some point, if you start increasing large number of CPU, for example, um, think about CPU or core as human. If you have two people in the room, okay, and they all can be healthy, versus you have like 10,000 people in the room. Chances are that within that 10,000 people in the room, especially right now that we have COVID, right, there would be high chance or high probability of someone will get sick in the more dense population there. So therefore, my hypothesis when I start apply this reliability aware in terms of scheduling, when we start scaled up the system to have 100,000 or even million cores. I mean, at the time when I start working 20 years ago, okay, we don't have these million cores. I think I show you when you go to top500.org, one of the largest machine is million core or 10 million cores there. So, but then we already anticipate the high growth of cores in large scale system. Okay, so in that case, we start working on or predict the failure, and then apply reliability aware scheduling in a way that we can achieve better result, complete the job. Because our hypothesis or theory, we state that the high number of core or component, the higher probability of failure. So therefore, if we can mitigate and find optimum number or segment the system in a way that we can improve reliability. So that link would point to one of my own papers with my previous student. I think right now he is as associate professor at ULL. Okay, work in Lafayette. Okay, so I think um, these are example of others scheduling policy which professionally I've been working on the scheduling weather algorithm for the past 30 plus 30 years or in fact 30 years. Now let's switch gear, guys. Let's continue on and discuss on um, instead of you have one ready queue. Okay. Now let's assuming that the system divide into multiple job queue or multiple ready queues. Okay, even though you may have a few cores, because right now system not only one core or one CPU, one core. You may have multiple cores in one CPU, and then large scale system you may have 4 to 8 CPU, and each CPU you may have uh, 8 cores or 12 core or 16 core. So one system you can easily, one of the largest, you can easily scale up to one system, meaning that one building block or server that when you put together a large scale system, because supercomputer or high performance computer, they don't build one gigantic system that 10 million cores there. They would build a system with perhaps one small server, and then they can network them together. So each server or node it may consist of 64 or 128 cores. Okay, but then that is main CPU cores. But some of them may also attach with the GPU. As you know that the high-end GPU like NVIDIA 1080 or 2080, some of them has 500 something cores, and then some GPU may have 2 GPU cores stitched together. So one card you may have end up with the GPU a couple thousand, I think we call stream processor or the cores there. Okay, but then with this each node, then they will connect with connectivities. Okay, so that it can form larger scale. Okay, so but that beside the architecture of supercomputer system. Now coming back to the current system, either your current desktop notebook or enterprise server. Some of the server may have up to 32 cores on one server or one system, or maybe 128 cores. I don't see the main cores like Intel or CPU that put together in one system larger than 128 core. The main issue is the system bus, because when you have more cores there, then the bus must be as capable as number of cores, because otherwise you will have the bottleneck that you cannot move data in and out. So the more cores you have, the higher bandwidth that you should have. But then if you're gonna if you're gonna design one system that has exotic system bus, then it may not be cost effective. As you know that the current commercial off the shelf, that you can go buy, basically, the most popular we call Intel bus system that has North Bridge and South Bridge. I cannot remember exactly the capability or the bandwidth of those system bus, either 6 gigabit or 16 gigabit or North Bridge or South Bridge. I think you can Google and take a look. But then coming back to instead of you have one ready queue, okay, some of the new system you may have 4 core, 8 core, so therefore it get more capabilities there, and therefore we can start divide the ready queue into multi-level queue scheduling, okay, where each queue you may designate for different type of activities. For example, in this picture on the top queue, you may apply more resources here, because in this case you may pin 2 cores here, or even though you have single CPU, you may allocate more percentage to higher priority process, such as system processing here. Or maybe if you have interactive process, you may have interactive but simply editing process, batch process, or student process. So in that case, instead of one single ready queue and then single CPU that we discussed, those are still valid, but we simplify the problem in a way that we can easily communicate and explain to you. But then let's say that if we start enhance the problem and then make it close to real world, we may end up seeing multi-level queue scheduling. Okay, so in that case, for example, maybe perhaps if total number of resources is 100%, we may assign the high priority is 50% of the total resource, 20% for interactive process, 10% for this interactive editing, and then 10% for batch, and then 10% for student. Okay. So now example of multi-level queue, perhaps you may have ready queue that partition into simply foreground or background, where each queue has its own scheduling algorithm. Let's say that the foreground queue, you may apply round robin, and then background queue or batch job may be perhaps using first come first serve. Okay, um, so the scheduling also, I mean, for each scheduling algorithm must be done in between queue, and also must be a mitigation that you may be able to migrate the job from one queue to the other queue. Okay, some scheduling algorithms such as fixed priority scheduling may lead to probably starvation. So therefore, you may apply aging solution. You can remember when we have a fixed priority scheduling, sometimes if that job queue is just so busy, the less fortunate or the longer job, let's say if you use a shorter job first, may not get service at all. So therefore, it may lead to starvation, and then we can use aging as um, a solution to alleviate starvation problem. You can remember, make sense? And then some queue you may apply the times like the round robin. So each of queue may get certain number of CPU resources, like 20% for round robin, and then 80% for foreground in round robin, and then 20% for background first come first serve. So these just are example or simplified example of how multi-level level queue works. Okay, and then also the as I mentioned. Okay, sometimes you may want to apply the adaptive in order to alleviate the unfairness or the starvation issue. So therefore, the process or the job can be moved in between various queue. Okay, by apply aging techniques. Okay, so that it will remove issue of starvation. And then multi-level feedback queue scheduling can be defined as following parameter. First, how many queues are there? Okay, ready queue. And then which are scheduling algorithm that you want to apply to each queue. Then what method that you plan to use to determine how to demote or promote or demote, okay, or upgrade the process. Okay, that's related to the aging. Which method that you use to determine when you want to demote. Let's say that if this process already has been allocated enough CPU but have not completed the job yet, then maybe you decide to demote this process, maybe based on certain ownership, or if this process is not necessary, and then you have more application or process that require more attention, then you may demote certain process and upgrade certain process. Okay, and then which method to determine which queue the process may enter, and when that process needs service. Okay, so that's based on the algorithm that you may want to apply. Okay, so these are 5 major parameter in which the multi-level feedback queue scheduling normally would require in order to make some decision. So the diagram look like this. Okay, let's say that we have 3 level queues, number of 3. Okay, the number here, the number of queue, which algorithm that we want to use, how to upgrade, how to demo. Okay, as well as how to enter the new process. Okay, and then when the process need some service. Okay, so example, let's say that if we have 3 queues, and then the first 2 queue we define time quantum. Okay, both Q1 The first queue and second queue both are round robin RR, where the first one, the time quantum is 8, because we want to give a little more attention, more resource, meaning that it will quickly execute. If not, then we context switch out. The lower number, the more context switching you're gonna see, okay, because it's gonna keep switching between each process, okay. And then the second queue we have round robin, but then each has 16. The time quantum is 16, okay. And then the last queue is first come first serve. That means in this case, when we have the new process arrive, okay, it will first enter, okay, the top queue, which time quantum 8. If it can complete the job, then it got demoted into the second queue, which has time quantum equal to 16. And then last but not least, if it cannot complete within 16 unit time, then it go down to first come first serve. However, each queue you may give different resources. For example, this one you may have 50% of total resource, and then this one you may have, let's say, 35%, and then last one you may have 50. These are not magic number. Some of these number can be engineered. Why? Because you can do a performance test, system test before you deploy your product. And then most of your system, okay, normally you can have normal workload, that's certain thing gonna come at certain time, and then you should be able to engineer the number of transaction or requests coming in, okay. So therefore all these can be engineered, and it would drive how to derive this number, okay. So I think, as I told you, when you start doing performance evaluation, okay, I think it's quite useful for your future when you start design something. It's not only you're going to design some architecture or diagram how each subsystem to interact, but also you need to start evaluate, analyze the performance implication, quality of services in a way that the machine or the system will have a nice flow of the requests and the process of those requests, okay, in a way that it would give optimal solution, okay. And all those are not based on the fluke or by chance. All those has to be analyzed, study, analyze, calculate, and engineer. Okay, so as I mentioned, some of these numbers we just make up, but then in fact, in reality, if you have the problem given to you, if you know, for example, how many transactions you're gonna have. Let's say you're gonna design something like Amazon.com. Well, I mean, a lot of time, the technical people, just like you or me, I mean, we don't know the business, but then we have to talk to the business people, product manager or whatever people who are responsible, financial officer or something, that they may predict the growth of the company, the current revenue that they expect to have. And then you can start mapping the financial requirement, meaning the growth of the company based on what you want to achieve. A lot of time, those finance people, they don't know this system, they don't know technical, but then they know that I'm gonna grow the company to be 1 million or 100 million dollars per year. Okay, so in that case, you need to start calculate back from $100 million. Okay, if you know your business, for example, if you are e-commerce like Amazon, what do they make money? How do they make money? Selling product. And then selling product, they can estimate that by average, they may want to make like $1 per order. Even though some of order they may make like $10, $20 or $100. I don't know. But then some of them they may make like $1 or $2. If they have done whatever this business for a while, they probably would know the average how much money they make per order, for total, if they divide by total number of order. So with that, let's say that if they make like $1 per order, and you want to grow like $100 million a year kind of company. So therefore, you're gonna have to sell, or you have to make like 100 million orders per year. And then with $100 million or 100 million orders per year, then you divide it by 12. So whatever those number, let's say that is 10 million orders per month. Okay, then you can divide by 30, which is per day, per hours, and then from that, okay, that each order, let's say that you have to handle 200,000 orders per hours. Okay, then you can start work back, okay, on those requirements and map to see, oh, how large database we have to decide how many virtual machine in order to be able to handle 200,000 orders per hour. Okay, so I think all and all that I try to kind of inspire you or convince you to work on the problem and understand the problem and map to an analysis model. Okay, it helps you in the future, especially if you want to grow to be a technical lead, if you want to grow to be the owner of the startup company. I mean, not knowing this, then you just close your eye and then throw the dart to the target. Okay, but then if you know all this, I mean, uh, potentially you would hit the bullseye easier than you just close your eye. Okay, all right, so let's move on. I think this is just repeated on the previous slide on the example on multi-level feedback queue. You have three queues there. Q0, the time quantum is 8 millisecond. The second or Q1 time quantum is 16. And then Q3, Q2, which is the third queue, is first come, first serve. Okay. The scheduling, once the new job arrives, okay, then we're gonna let it enter Q0. Okay. The Q0 is applied similar to first come first serve, but it's round robin because we keep time slide is 8 units. As I told you, round robin, it looked like first come first serve, but it preemptive. Okay, where we define time quantum or limit time on CPU. So in that case, if the first job, the new job cannot complete within 8 milliseconds, then we will demote it. Okay, move down to Q1, where Q1 again, serve as round robin, but with time quantum is 16. Okay, so in fact, when it say first come first serve, it's true, but not 100% true. Okay, because if you have first come first serve with limit time, I think it in fact those technique I think is more, it's better to call round robin. Okay, so then if it demo to Q1, if it cannot complete within 16 milliseconds, then it will preempt and then move to Q2. Okay, so it will go down and down. But then you said that, wow, why do you call it demo? What? Well, even though it got more time, but then as is you take a look, or I already hint you previously, Q1 you may get more attention to Q1 where you allocate more resources, maybe 50% on Q1 or Q0, and then 35% of resource to Q1, and then 15 to Q2. So in that case, I think all those numbers that I think is not the main point. Those numbers would based on how do you engineer, how do you calculate, and how do you analyze your system. Make sense, guy? So I think this is just another techniques on multi-level feedback queue. I think let's move on. I think we have two more and then some example. I try to complete our chapter 5 lecture today. So now, in terms of multiple processor scheduling, the scheduling is more complex, okay, because it's not only one CPU, one core. You have multiple CPU, and then those multiple CPU has multiple cores, okay, and some of these multiple processor system, most of them are homogeneous processor, okay, in multiprocessor. So in that case, it's not that difficult. I think imagine that if you have m number of processing or job, and then you map to n number of cores or processor, n to m mapping. If you want to do algorithmic type of scheduling algorithm, okay, it's gonna be NP complete problem. Okay, I think you will hear this term NP complete problem when you are taking 311 or theory of computing. Okay, it's a non-deterministic type of problem. So in terms of optimal solution, it would be NP complete, meaning that it would take too much time to determine. So then a lot of time people apply heuristic in terms of instead of algorithmic. Okay, for example, the heuristic could be, for example, first come first serve is heuristic. Okay, or the shortest job first could be heuristic. It may not necessarily optimum, but it could be optimum. Okay, but based on certain criteria, then we make some decision. Some of the system, okay, that instead of you schedule the job into one server or one node, you may schedule the job into multiple nodes. So in that case, you may have load sharing or load balancing, okay, module or subsystem in front that will start distribute to different node, okay, and then each node then it will has the native operating system schedule the job to run on each node, okay. For example, if you are familiar with Amazon Web Service or AWS, where you can buy cloud computing resources like virtual machine, it has elastic load balancer that it would be a front end where if you want to scale it up, okay, then it has ability to distribute load to different virtual machine, and then each virtual machine will use native CPU scheduling, schedule those jobs. All right. Um, Now let's talk about real-time scheduling, okay, which is it the same scheduling technique could be applied to, but then it has an extra requirement with respect to real-time scheduling. Most real-time scheduling apply to embedded system, apply to a mission critical type of system, such as computer control car, automation, self-driving car and all those. Okay, so if someone want to look into a self-driving car and then with respect to real-time scheduling or operating system aspect, that could be term paper presentation. Okay, in fact, we have one of our previous student who graduated probably 2007 or 8. Okay, his name is Sugar, originally from Nigeria, but I think it's quite smart student. In fact, he's one of the best operating system student that I think he later on graduate and then work from somewhere and then went to start his own company in Silicon Valley. And then later on, I'm not sure he saw the company successful or not successful. He worked for Cloudera, which is one of the top cloud computing tools, in the market or in industry. And then last 2 years, he moved to Lyft, which is similar to Uber, and then he's the Lyft autonomous car team leader that working on whatever it is, self-driving vehicle project. So I think I could hook you up with this guy, and um, I think let me see whether sometime I invite some of our previous students to do some presentation with this online kind of thing. I think we need to figure it out. So, but let's come back to this real-time scheduling. Okay, there are two class of real-time scheduling. Okay, the typical one we call hard real-time system that require the complete of critical tasks within a guaranteed amount of time. So this is the keyword. Okay, so for example, the smart bomb, the computer controlled smart bomb is a hard real time. If you want to launch the mission and you cannot guarantee, the calculation, the trajectory, and all those kind of things, then you should not allow the mission to be launched. Okay, so I think therefore some critical type of situation that you apply computer control. Okay, they must acquire or impose with the hard real time. The completion time of the task, okay, is guaranteed. That is the main key of the hard real time. Versus the soft real time computing, which is relaxed. This guarantee the critical task to guarantee amount of time for completion. It requires the critical process receive priority over the less fortunate one. Okay, that means you can preempt the less fortunate, which is previously if it's mission critical, then you have to see is it real critical or not. Okay, if the situation is all everyone is equally critical, then you must have to apply the hard real time. Otherwise, you can use soft real time computing. So in terms of soft real time computing, the total response time that you have to factor in beside the actual real-time processing is the dispatch latency, okay? Because, I think if you're gonna preempt one process, you have to perform context switching. So in that case, you have to interrupt that process, okay? And then, you start save software state into PCB, resolve the conflict, okay? And then resume that process execution or start that process execution. So these are the total calculation with the total response time, okay? I think I just want to kind of highlight and show you more complete pictures, okay? Does it make sense, guys? Okay. All right. Now, I think that's what I told you. That is the actual real-time process execution, but then you have to add up the dispatch latency, okay, which is, it could be significant. Um, as I told you, part of context switching or dispatch latency, these are activities that you have to save and restore the process information to and from PCB. So therefore, it requires quite significant, sometimes quite significant overhead there. I think you already seen this picture multiple times. As I mentioned to you, this patch module is the module in which is control or enable context switching. Okay, so these are the following activities that we already talk about. Context switch, um, switch bit mode, and jump to proper location. Okay, now to evaluate all these scheduling algorithm, okay, then I think you can work on whatever I just show you, we call deterministic modeling or applied queuing model. So in that case, you can take a particular predetermined workload and define the performance on each algorithm that we already covered this, okay, and then somehow you may apply queuing models, and then last but not least, you may implement and evaluate at the final product. But I anticipate that in near future we may be able to take this data, okay, that means we collect all these activities, how much time this application use CPU, the execution time or whatnot, and then apply machine learning or AI. So then you can predict the CPU burst with the load pattern, and then schedule the job in a way that it's more smart. Okay, so I'm foreseeing that AI or machine learning could play a significant role in operating system in terms of self-tuning, self-adapting. Okay, does it make sense? So anyone who work on AI for OS, you can touch upon on this scheduling as well. And I think this picture just show somewhat, evaluation of the scheduler by using some simulators or simulation. So you can write some simulator and then feed the workload pattern. I mean, for each of these techniques, like first come first serve, shortest job first, round robin with different number. Okay, and then you can evaluate the performance, collect the performance statistic, okay, or whatnot, and then compare them. Make sense? Okay. Um, with respect to Linux process scheduling, okay, I think it has a few techniques that normally the standard Linux kernel will apply. Either it applies soft real-time first come first serve or round robin, or it may also apply the time sharing with priority prioritized credit base. Okay, if you guys are Linux type of user, okay, there are some commands that you can change. In fact, once you launch the job, okay, if you want to change the priority of given process, there's a command called nice. Okay, so let me go to the terminal and then show you the command. Let's say that if you say command man nice, okay, nice is a command that or utility that you can change the alter the scheduling policy. I can demonstrate to you right now because I think with whatever I have to log in as the root, and I don't want to mess up my um, presentation today, okay, but there's a command called nice, okay, as Linux utility that you can change the parity of the Linux or Unix, okay. So let's move back to I think we're almost done, we have 2 more minutes left. um, anyway, so I think this is example of Linux process scheduling, okay, that I think it apply. It's not necessary that you have only one algorithm or technique. You may apply multiple techniques there, but I think in terms of the kernel, I think you have these various one that we show you on the screen here. All right, okay. And then this is showing Solaris, which is already outdated. Solaris used to be one of the top hardware or computer, model that market by Sun Microsystem. Okay, so I think Sun Microsystem is no longer exist because Oracle bought Sun, and in fact, Sun used to be like Dell or HP computer like today. Okay, but I think with a few missteps. Okay, in fact, if you guys are Java programmer, Java is invented by one of the Sun founder. I think Bill Joy and the other guys. Okay, but I think doesn't matter. You don't have to remember this, but I just want to show you that it apply various scheduling techniques, just like real-time interactive sharing using different class of schedulers here. Okay, I think that's it. So again, I think this is the conclusion of today's class. I hope that if you don't follow me, please go back and review. You have some question, we can schedule a face-to-face meeting through this either Skype or a Zoom conference call. Okay, and also just quick reminder that I think I will um, I will post the I will post the question, the quiz by tomorrow, and then please make sure that you all do the quiz by um, midnight on Sunday, April the 5th. Okay. Also, the title of your term paper presentation is due by tomorrow by midnight. Okay. Send me some. If not, then by next Tuesday, I will tabulate what I have. Okay, and then I may assign similar topic or whatnot. Okay, and then everyone should be able to start do some reading or study and then get ready. My expectation, I'm gonna write some description about expectation from this term presentation. Okay, like I think you need to have some sort of PowerPoint or PDF to you can share the screen during presentation, and then we're gonna do a Zoom conference call so that it can be interactive. All right, okay. So other than that, you all have a nice day. Okay, be safe and let's hang on, working together. I think we're gonna fight through this challenge time and then come back with stronger. Okay, so other than that, please take care and see you. Okay.